Okay, this is the second part, the second lecture on Chapter 4, Summarizing Data Graphically. A picture is worth 1,000 words. So I want to start off talking about a population of interest here in Humboldt County, the king salmon. We've had historically, Humboldt, this region off the coast here, has been one of the top salmon producing areas in the world, for king salmon at least, but for various reasons the fishery has been in decline, as some may know. In any case, I thought it would be interesting to take a look at an example. So let's start talking about the data here. A field biologist working for the California Fish and Game recorded the following weights for 33 king salmon caught by sports fishermen fishing out of Humboldt Bay. And here we have a data set. First thing I want to talk about, though, is the difference between the sample in our data set and the actual population. And one of the questions we can ask ourselves is maybe how many salmon are out there? And I think the answer is a lot. Many salmon, thousands and tens of thousands. And I'm not sure of the number, to be honest with you, but there are many, many salmon out there. And since this is a measurement, since these are measurements, one of the things that we have to keep in mind is that the data is continuous data, and meaning it comes from a variable, or it's based on a variable. I spelled continuous wrong. Continuous. So it's based on a data that's continuous. And again, I know that because it's a measurement. So if I think about how I would graph the population, essentially what we would have to do, again, I'll label the variable, and I'm labeling it x, and x is going to be, I'll define x down here, x is equal to the length of a randomly selected king salmon. So if I'm going to think about what the graph of the population, again, I'm talking about the population here first. If I wanted to think about the graph of the population, one of the things I need to consider is what's the smallest possible salmon length? Well, you might argue 0 would be the smallest, and then we could come up here and talk about what the largest would be. And I don't really know. That's a tough question, but I do remember when I was young. I grew up in Humboldt County in Fortuna, and I do remember when I was young seeing that a woman actually caught an 82-pound salmon under Fernbridge. But this is way back. I mean, this is back in the 80s. So I don't know if there are fish out there, king salmon out there yet, still that big. It's really hard to say. But but in statistics, when we deal with populations like this, we don't really have any way of knowing. We can't measure every salmon out there in the ocean, so we have to make assumptions. And part of those assumptions are built in how we model the population, or what graph or function we're going to use to describe the distribution of that population. But I'm not really interested in getting too deep into that, because the main ideas in Chapter 4 are ideas about graphing data, really. But I think it's important to go back and think about what the shape of the graph would look like for the population. Now, I'm doing a pretty bad job at drawing this graph, granted, but what I'm trying to draw here is a bell-shaped curve. Okay, so one of the ways that we would model a continuous population like this is with a bell curve. And this is a continuous curve. And it has to be continuous because the data is the variable is continuous. So let's come now and talk about the data for a second. When I'm drawing a data set, really what I need to consider is the range of the data. So we'll use the variable as it was defined in the previous example. And I'm going to go over and take a look at my data. And what I see is I've got 9.88 looks like about the smallest data value here, and 47.28 looks like about the biggest. So if I started at 5 and went to 50, I should cover all the data values. So now I have a scale on my axis. And what I'm going to do, first of all, first graph I'm going to draw, just to kind of go back to chapter 1, where the very first type of graph we drew, or type of graphs we drew, were called frequency plots. And in fact, I could draw a frequency plot of this particular data set. And here's how I do it. I'm just going to go through the whole data set now and kind of estimate about where those data values would go. So that I'm going to call that about 32.7, 17.86, 45.26, 29.43, 36.32, it's right about here. $34.02. So you can kind of see I'm sort of getting in trouble here already with my scale. There are definitely clusterings that are happening here, but notice how one of the problems is these x's aren't really stacking up on each other because, again, none of them are exactly equal. So I can't really put x's on top of each other. When we were dealing with discrete data, we could recall that we could actually stack those x's up, and it made more of a shape to the distribution. So really, frequency plots are best for discrete data, and not so good for continuous data. So I'm not going to continue on with this here, but what I want to demonstrate, what I want to talk about is a different type of a graph, really, which we call a histogram. And when we draw a histogram, what we do is we add a second axis. And this is going to be the frequency axis. And on this axis, I'm going to maybe put 5, 10, 15. I probably have more, my scale up here I probably made too big, but that's okay. I'll just go with it here for now. And so what I could do is I could say, okay, how many of these data values are between 5 and 10? So I'm going to go through my data set and just look here and see how many. There's 1. How many are between 5 and 10? All right, it looks like 1. So if I made a bar here that's about 1 unit tall, that would represent the frequency of data that's between 10 and 15. I'm sorry, between 5 and 10, I mean. And now I'm going to look for data values between 10 and 15 and count those up. So I've got, let's see, between 10 and 15. So I don't see any. So I'll go to the next class. How many data values are there between 15 and 20? 1, 2. Wait a minute. Oh, shoot. I missed that one from the previous. That's actually one between 10 and 15, isn't it? So I missed that. So let me go ahead and draw that bar there. We'll go back and start over with 15 to 20. So let's see here. 15 to 20. So there's 1, 2, 3. Looks like about 3. So the next bar I would make about 3 units tall. Do the same thing here for 20 to 25. So let's see. 20 to 25. All right, I don't see any there. So what about 25 to 30? There's 1. 25 to 30. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like we have 10. Oops, I want to go up to 10. It looks like I should have made my upper max here about 10 instead of 20. But again, I just want to demonstrate the idea behind how we draw the histogram. And what I would do to finish drawing this histogram is by hand is just finish drawing those bars. But what I really want to show you how to do is how to draw this on the calculator, because again, drawing these graphs by hand is really cumbersome, and obviously it's quite easy to make a mistake. So let me go here and start up the calculator. Let's see. I thought I had the calculator here. Where'd it go? All right, oh, it's back there. All right, let me grab. All right, so here's the calculator. And what I want to do is, first of all, I want to show you how to enter this data into a list on the calculator. Okay. So I'm going to go into the list editor. So first thing I'm going to do is press Stat. I'm going to choose Edit. Okay. And the list I'm going to use is L1. So I'm going to move my cursor all the way up to the top here of L1. And again, you can use any list you want. It doesn't matter. As long as you remember where you put the data, that'll work fine. So I have some data in here in L1. So I'm going to move my cursor all the way up here to the top, and I'm going to press Clear. Then I'm going to press Enter. Okay. Now, the cursor is where it needs to be. It is within the body of the cell here. You don't want your cursor up here highlighting L1. You want to right down here in the body of the actual table. And basically what I'm going to do is enter each of the data points one at a time. So let's take a minute and we'll do that. Oh, and I hope you have your calculator out too so you can follow along. Okay, now I have all the data entered into the calculator. So we'll go on to the next step. The next step is to set up the stat plot window. So notice up here above the Y equal button on the very top row of the keys, you'll see stat plot. So we're going to press second Y equals. Now there's three types of stat plot, or there's three different stat plots we can configure. Okay, so we can draw multiple graphs at the same time. But that's not our interest right now. I just want to take a look at a histogram for the data set that we're talking about. So I'm going to select number 1, and it takes me into another window. So the first row here, what we have is an on-off switch. And since I want to actually draw this graph, I'm going to select on. And then the next thing we have to do is choose the type of graph. And there's 6 different types of statistical graphs the calculator will draw. This is the scatter plot, the first one. This is a line plot. We have the histogram. We have 2 other ones down below called box and whisker plots. One's called the modified and one's called just the standard. And then we have the last one here is called the normal quantile plot. But again, we're interested in drawing a histogram. So I'm going to leave my cursor here on the histogram. Then the next thing we need to do is identify the X list. In our case, we are using list L1. Again, we can name a list for our data and draw a histogram of a named list. But for this particular data set, I chose to use L1. So what I'm going to do now is press, with my cursor right on X list, I'm going to press second 1, which corresponds to list L1 right there on the keyboard. So L1 gets pasted in. Now we're set to go with the stat plot window. The last thing I need to do is configure the actual window for the graph. So if you look here, again, on the top row of keys, this button right here is called the window key. And this happens to me sometimes when I normally, yeah, it's not going to work. All right, so what I have to do first before I can go to window is go second, quit, to come out of that Y equals menu, and then go to window. All right, that worked that time. So what I want to do is set up the same scaling that I had on my previous graphs. So I went from 5, on my previous hand-drawn histogram, I went from 5 to 50, and the X scale is 5, okay? Now, for a histogram, X scale defines what we call the class width. And one way to think about that is what number are we counting by on our x-axis. So if you recall, the x-axis I used counted by 5s. It went 5, 10, 15, 20, so on. So when I go from 5 to 50 by 5s, that's going to establish the same bar width and the same scaling on the axis. So now I'm going to think about the y values. Now remember that vertical axis is measuring the frequency with which data occur within each one of the classes. So the previous graph, we started off at 0 and we went up to 20, but I think that was really more than we needed. So let me just make y max 10, and again, I'll count by 1s for the y scale. All right, now I'm going to press graph. And notice what we see here is a histogram. And I can see also I made a mistake because I must have missed a data point here somewhere because the calculator actually, or I might have entered a data value wrong. I'm not going to get too hung up on that really. If I didn't enter a data value wrong, that means the histogram I was drawing by hand was wrong. And again, it's very difficult sometimes to draw these things by hand. You have to be very careful that you're getting every data value where it belongs. The nice thing about the calculator is it really doesn't make those kinds of mistakes. Now, notice that this graph on the calculator has no numbers, it has no label. And that's really a problem. One of the issues with the calculator is that the screen doesn't really have a very good resolution, and so there's really not enough room here on the screen to put the numbering and the letters and the labels on the axis. But what we can do is use the trace feature. And notice when I hit trace, it shows me the boundaries of the class, 5 to 10 for the first class, and then the number of data values. There was 1 data value in that class. And I can arrow to the right and see all of those particular boundary values, 20 to 25, and then N tells me what the frequency is for the data within that class. And again, I can just scroll across and look at the height of each one of the bars. Now, a nice way to do your homework, I think, is to actually go ahead and enter the data from the homework problem in the calculator, draw the graph, and then just sketch it onto your homework. because again, once you set up the scaling on the axes, you can just use this trace feature with the histogram on the calculator and know exactly how high to make those bars. So that's kind of a nice technique. Let's talk about a different kind of graph here now. This is the next kind of graph I want to talk about is called the scatter plot. And the scatter plot is using two variables here, okay? We have one we could call the predictor variable, and maybe we'll call that x. And we have another variable called the prediction or the response variable. And this terminology will come up throughout the semester. So to draw a scatter plot, what I need to do is, again, I'm going to create two axes. I'm going to create an x-axis, and I'm also going to create a y-axis here. And again, I want to think about the scaling. So this is going from 20 to 100. So I might start this at, let's see, I might just start this at 0 and call this 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So I probably could have stretched that out a little bit. I was sort of stretching it out as I went along, but nonetheless, we'll just go with it. And then the proportion of cars here will be the y-axis. Now, one of the things that we might, I started this one really at 0, even though the first data value is going to be at 20. I really like having 0, 0 as the origin for the axes, because what can happen is, depending on where we start this axis here, we can distort what the data actually looks like. However, the smallest proportion here looks like it's about 55. So it wouldn't really make sense to start this axis at 0 because, the first data value would be way up here. And so what we can do is actually indicate that we're going to put a break in the graph, and then maybe start the graph at, say, 60 here, and then go 70, 80. Again, let me go 65, 70, 80, or 75, I should say. I'm counting by fives now. 75, 80, 85, 90, and 95. And so this first set of data, 20 and 60, are going to be an ordered pair on the graph. So what I would do is go to 20 on the x and 60 on the y and put a little dot right there to indicate this particular pairing. So again, this is we would think of this as like the ordered pair 20, 60. Then the next one's going to be an ordered pair of 30, 55. So again, I go to 30 here and then up to about, 55. Shoot, I started that at 60. I should have started it at a different place, huh? Kind of messed this one up. What should I do? My eraser won't work. So let me just actually, I'm gonna go ahead and start that over. Let me just give me a second here. I'll rescale this. That and 1,000. Put a little break on that one. So let's see. And there's nothing wrong with redrawing your graph when you make a mistake, or Okay, so there's a scaling that might work. So let's see, starting at 20 here, I could go to, let's say I'd put a point here at 60, and then 30 corresponds to 55, and 40 corresponds with 75. So again, let's draw a sketch here. 50 corresponds to 85, 60 corresponds to 84, a little bit lower, 70, 97. See, and then 80 corresponds to 86. 90 corresponds with 90. And 100 corresponds with 95. So that's kind of a rough drawing, and you can see there looks like there's a pattern here, an increasing pattern in the data, and we're going to talk about this kind of a pattern in chapter 13. So it's called a linear, we would call this looks like a linear, positive linear relationship. Again, that's a linear regression topic. I also want to talk about how to draw this graph using the calculator. So let me, because again, you know, drawing it by hand is kind of less accurate, and calculator is really a nice way to go here. So let's see, let me get the calculator up, and so I can also see the data. And so this time what I'm going to do is I'm going to go back to the editor. So I'm going to press Stat and then choose Edit. And this time, I'm going to use L2 and use L3. I could use L1 and L2, but I've got that salmon data in L1. And in fact, you know what? I have an idea. Let me show you. Let me just go. I was in the middle of clearing that, so let me finish that. But let me show you let me show you how I would take this data that I've entered and put it into a name list. And that'll free up L1 for me to actually use L1 and L2 instead for this example, and it's worthwhile in doing. So what I'm going to do here is I'm going to create a name list. I'm going to copy the data in L1 into the name list, okay? And so what I want to do is go first of all, notice I've moved my cursor all the way up here to the top, okay? So the first thing I did was I arrowed all the way up to the very top. So I want my cursor all the way up and have L1 actually highlighted. So you want your cursor all the way up here at the top. Now I'm going to go second, delete. What that does is it inserts a blank column. And I want to give this list a name. Notice the A in the cursor means the calculator is alpha locked. So I might call this K S L M N. I don't know. And again, there's other ways you can abbreviate things. The calculator only allows you to have 5 characters for a list name, though. So now I'm going to press Enter. Now I have a list name King Salmon. Now notice the calculator automatically is ready for me to put a whole list there, assuming that I've got something in L1 or something like that that I want to rename. And that's actually what I want to do this time. So I need to press Enter so my cursor comes down to where this equal sign is. And I can press second 1 for L1 and then press Enter. So now I've just copied all the king salmon data into a list, a named list. And again, that frees up my L1 so I can actually use it for the next example. So here I've highlighted, I've put my cursor all the way to the top again. I want to clear out the data, so I'm going to press Clear and then Enter, and now that data is all cleared out. I'll enter the family income into L1. Then I'm going to arrow over to L2. It's ready to go, and I'll enter the proportions. Now remember, I want to keep the order of the data values I'm putting in intact. Okay, in other words, this is paired data, so I never want to sort this data or do anything like that because I would lose the dependency relationship between the actual data values if I sorted. And when I go to do a scatter plot on the calculator, what the calculator is actually going to do is it's going to look for the pairings between the two lists that I'm drawing a scatter plot of. So again, first step in drawing the scatter plot is to enter the data, and I've already done that. So now I'm going to go in and press second y equals to take me to the stat plot window. And I'll press enter here to choose plot 1. And now I'm going to change it from a histogram to a scatter plot. Now watch what happens when I press equal. Okay, it now is asking for an x list and a y list. So the calculator knows when you're drawing a scatter plot that you need an x list and a y list. So L1 is what our x list is. What I need to do is to come in here and change this other named list to L2. So I'm going to actually clear that out. I'm going to press second 2 for L2. Okay, and now I need to set up the window again. So this time I'm going to go second quit and then go to window. And I want to, again, think of the scaling here. So the X data is going from about 20 to 100. So on that scale, you know, I could go from 0 really to say 100, I suppose, or 105 maybe, just to give some extra room on the axis. Counting by 5s on that axis makes sense to me. And then I'm looking at the scale for the proportion here. 55 looks like the smallest, so maybe for x min, I'll make that 50. That should be small enough to capture the lower data values, the lowest data value there. And then 97 looks like the largest one, so x max of 100 makes sense here. And maybe for at y scale, I'll look at counting by 10s. And again, there's more than one way to draw these graphs. This is just my particular choice for the scaling. And now once I have those that window configured, then I press graph and I can see the scatter plot. And again, we can do a trace to see what the particular numerical values for each one of the data values is. So again, the calculator is really good at drawing these graphs. The only downside again is that it doesn't put numbers on the scaling for the axes and it doesn't label the axes. We kind of have to know that. One thing though it does is it shows us that we're looking at plot 1, that's what P1 means, of list 1, L1 and L2. So it does print out up here in the upper right hand corner. Now the 83s don't actually do this. There's actually under format here, there's an option to turn the equation on and off in the graph. So you may or may not see that, but in any case, I'm not going to cover that in this lecture. So that's the scatter plot. All right, let's talk about a few definitions here. So studies are often conducted to attempt to show that some explanatory variable causes the values of some response variable to occur. The response or dependent variable is the response of interest. That is, the variable we want to predict, and is usually denoted by y. The explanatory or independent variable attempts to explain the response, and it is usually denoted x. So this is really reminiscent of algebra. And in algebra, we call the y value the dependent variable, and we call x the independent variable. So that's sort of algebra language. And in statistics, we use a different language. We call the y the response and the x the explanatory, because the idea is y is responding to the values of x because it depends on x. And a scatter plot shows the relationship between two quantitative variables, x and y. The values of the x variable are marked on the horizontal axis, and the values of the y variable are marked on the vertical axis. Each pair of observations, x sub I, y sub I, is represented by a point in the plot. Two variables are said to be positively associated if, as x increases, the values of y tend to increase. And that's what we saw in our last example. Two variables are said to be negatively associated if, as x increases, the values of y tend to decrease. So we have positively associated and we have negatively associated. When a scatter plot does not show a particular direction, neither positive nor negative, we say that there is no linear association. All right, here's another kind of graph. This is a really nice graph. It's a fairly quick and easy graph to draw. And again, the purpose of this particular type of graph is to show the particular shape of the data set we're looking at. So what we're looking at here is data which are the percentage gain and per capita personal income by state. So the first data value I'm going to consider is 5.1. And to draw a stem and leaf plot, what I need to do is figure out how is this going to look best when I draw it here on this axis. And there's different ways to do this, but for this example, it seems like it makes sense to split the number up based on its decimal, okay? So what we would do is first establish the legend that tells us how to interpret the graph. So 5 line 1 represents 5.1, and so that will tell everybody that's reading our graph how to interpret it. Next thing I need to do is figure out what am I going to put here on the left-hand side. Now this is the stem over here on this side. And kind of scanning through the data, I see there's a 2.4. I'm looking for the smallest data value I can find. There's a 2.4 there. Anything smaller than a 2.4? I don't see anything. So one way I might draw this graph is to put a 2, a 3, a 4, and a 5. Okay. And again, this isn't the only way to do it. There are other ways. Oh, and then I got to get all the way up here to 10, I just noticed. So I'm going to go 6, 7, 8, 9, and 10. Okay, hopefully that's enough. And what I'm going to do now is go through the whole list of data sets. And I'm going to put the leaf part over here. So there's 5.1, 3.1, 5.1, 5.6, 2.7, 3.9, 4.4, 4.5, 5.0, 5.2, 2.4, 4.1, 5.4, 6.1, 10.9, 5.3, 5.4, 6.3, 4.7, 4.3, 4.9, 8.5, 0, 4. How many people want me to be quiet now? All right, so again, you can kind of see the basic shape of the distribution here. Looks like it's sort of mound-shaped and somewhat symmetric. We can see that these values between 4 and 5 show the most common range. And we're asked to describe the shape of the distribution. Is it roughly symmetric? I'd say yes. It's not distinctly skewed. What's the approximate center of the distribution? Well, the center of the distribution, I'd say, is right around here. And when I think about the center, I want to think about, where would that balance point be? So the center of the distribution, I would say, is somewhere right around maybe 4.4 or something like that. And that takes us to the discussion about these different shapes of distribution. Okay, this is, again, the bell-shaped curve, or the normal curve, and it is symmetric. It has a line of symmetry right here. And it's unimodal, meaning it has one peak. Um, and it's one of the really commonly used distributions in statistics. Here's another kind. We call this bimodal, and the reason is the mode is the most frequently occurring data value. But this is really, we call these distributions bimodal because there are really two mounds here, or two peaks. And we would describe that as by calling it a bimodal distribution. Now, it's interesting to note that this skewed looking distribution with kind of one side that comes up steeply and then the other side tailing out, we call that a skewed distribution. And we can get specific. This one we say is skewed to the right. Now the reason we say it's skewed to the right is because these points down here on the right-hand side are exerting more leverage. If we were thinking about rotating this distribution, right? This is sort of the physics analogy. And so the fulcrum would have to get this thing to balance, the fulcrum would have to move to the right. Because again, these values out here in the population are pulling down more than the values in close. And so we call it skew right because it's where the balance point, it's which direction the balance point of the distribution has to be moved to get it to balance. So this one's skewed left because that balance point would have to go to the left here. Now in uniform are really basically just a flat line like this across the top. And what that says is that every x value down here on the x-axis has the same chance of being included in a sample. And we say that we've used this distribution before because random int samples from a uniform distribution. It's just the domain of that distribution isn't continuous, it's discrete. It's a set of integer values. So let's go through this one more time. Symmetric, the distribution can be divided into two parts around a central value, and each part is the reflection of the other. We have unimodal. It means the distribution has a single peak that shows the most common value or values in the data. Bimodal, the distribution has two peaks. This often results when two populations are being sampled. Uniform is when the possible values appear with the equal frequency. Skewed means one side of the distribution is stretched out longer than the other side. The direction of the skewness is in the direction of the longer side. All right, well that does it for this lecture. See you next time.